motion of free electrons in a metal wire. When there is no potential difference applied across a wire, the free electrons are in random motion. When a potential difference is applied across the wire, the electrons move towards the positive terminal. You can see that the direction of the conventional current is from the positive terminal to the negative terminal.
Inside every battery or dry cell, it is the chemical reaction that provides energy to produce a charge separation. If the two electrodes are then connected with a conductor and a bulb, the result is a simple electric circuit in which a flow of electrons occurs. The chemical energy stored in the dry cell is transformed into heat and light. We can also represent the dry cell like this. The electrical charge flows past a specific point in the circuit at a particular rate. This is called current and is measured in amperes. Since electrons are so very small, charge is measured in coulombs. A single coulomb of negative charge consists of 6.25 times 10 to the power of 18 electrons. When 1 coulomb of charge passes a specific point in the circuit, each second, the current is 1 ampere. Current, however, isn't the only important characteristic of a circuit. You can see that the current flowing through both bulbs is the same. Yet, one bulb is glowing more brightly than the other. That means that in the circuit with the brighter bulb, each coulomb of charge must transfer more energy to the bulb, compared to a coulomb in the circuit with the dimmer bulb. To understand how this is possible, let's consider a comparison. Suppose a lone skier allows a lift to convey him to the top of the slope. In doing so, he acquires what we call gravitational potential energy. But what if he makes a wrong turn and ends falling off the edge of a cliff? When the skier leaves the edge of the cliff, the gravitational potential energy he gained in rising to the top is converted to kinetic energy as he falls to the snow below. The skier himself doesn't change as this energy transformation occurs. In actual fact, the gravitational potential energy we have assigned to him is made possible by his position relative to the Earth beneath. If the Earth were to disappear, he would not have that gravitational potential energy and would therefore not have to worry about falling. But the Earth doesn't disappear. So, what about the end of the fall? What has happened to the energy? The energy has been used to do work to compact the snow in the drift. Now, suppose that instead of a single skier, there are a number of skiers. As it was before, as each individual skier moves up the slope, he gains gravitational potential energy. This time, however, each skier comes down more sensibly. The gravitational potential energy is only partly transferred to kinetic energy. Most of the potential energy is depleted to do the work of throwing aside the snow. As we watch this cycle, we can see that energy is being transferred from the ski lift motor to the skiers, who in turn transfer it to the snow. Now we can view an electrical circuit in the same way. Instead of a ski lift, we have a source of electrical current, such as a dry cell. Instead of a slope, let's use a length of heating element from a device like a toaster, connected to the dry cell by wires. Instead of skiers, we have coulombs of charge that are going around the circuit. Just as a ski lift gives each skier gravitational potential energy, the chemical energy in the cell gives each coulomb of charge some electrical potential energy. The gravitational potential energy of the skiers was used up moving snow down the slope. As the charge flows through the heating element, the electrical potential energy is converted to heat. At the top and bottom of the slope, a skier may often glide without losing potential energy. Similarly, the connecting wires are chosen to allow coulombs of charge to pass through, with little loss of electrical potential energy. Now, consider 1 coulomb of charge. The amount of electrical potential energy this coulomb loses as it flows through the element from A to B is significant. The potential difference is the amount of potential energy lost by each coulomb of charge between A and B, often stated as the potential difference across AB. Potential difference is measured in volts and is given the symbol V. Potential difference is equal to the energy in joules transferred by each coulomb of charge. Suppose in this example we find that 3 coulombs of charge flowing through the heating element cause the element to give off 4.5 joules of heat energy. We can calculate the potential difference between A and B using our equation. So, in this circuit, each coulomb of charge loses 1.5 joules of energy as it flows from A to B. Since potential difference is measured in volts, we can say that the potential difference across AB is 1.5 volts. The potential difference in volts can be measured between any 2 points, such as these, or these. If the wires DA and CB are good conductors, there is no potential difference between D and A or C and B.
We talked about potential difference in current, but how are they related? The Ohm's law, which is probably one of the most fundamental laws of electricity, explains this relationship. George Simon Ohm, after whom this law is named, was a German physicist of the early 19th century who spent many years researching on the factors that affect current flow in a battery. He found that the current in a steady-state conductor is proportional to the voltage between the ends of the conductor. So if V is the potential difference of this conductor from point A to point B, and a current I flows through it, I is proportional to V. What Ohm also discovered was that current is inversely proportional to the resistance offered by a conductor. What is resistance? Imagine a river flowing downstream from a mountain. The river will encounter several rocks and boulders which will block its flow. In other words, the rocks act as a resistance to the flow of the river. Similarly, conductors also offer resistance to the flow of current. So if R is the resistance of the conductor, I is inversely proportional to R. Combining these two terms, we get I is equal to VR or V is equal to IR. The reason why we represent Ohm's law as V is equal to IR is because it's a lot easier to print in textbooks and reading material. Let's dwell on this resistance a bit more. There are 2 kinds of resistances offered by a conductor. The first type is to do with the material of the conductor. As the free electrons travel through the conductor, they also experience a force from the positively charged nucleus of the conductor atoms. This force of attraction resists the flow of current. The attraction force is more in certain conductor materials and less in other, depending on the type of atoms they're composed of. The size and shape of the conductors also affects the resistance they offer to current flow. Instead of having a conductor of length L, let's take a conductor with double the length 2L. This now means that the electrons will have to travel double the distance as before. Double the distance means double the number of positively charged atoms to deal with along the way, hence in effect doubling the resistance offered by the conductor as a whole. The cross-sectional area also affects the resistance. Imagine 25 cars at a signal, all moving through a two-lane, one-way street. The traffic can move pretty fast now as there's lots of space for the cars to move. But what would happen if those same 25 cars had to go through a one-lane street instead? The traffic won't move freely anymore as we have only one lane instead of two lanes. Similarly, when we cut the cross-sectional area of the conductor by half, we are in effect reducing the movement space of the electrons by half and doubling the resistance. So if we sum all this up, R is proportional to the resistivity of the conductor material, which is denoted as ρ. R is proportional to length, and inversely proportional to the cross-sectional area, as decreasing the cross-sectional increases the resistance. Hence R is equal to ρ times L divided by A. R is quantified in ohms, named after the person who discovered it. So our V is equal to IR relationship can now be rewritten as V is equal to I times ρ times L divided by A.
Let's have a discussion about laws of resistance. Let's think about a current-carrying conductor which carries a certain current at certain voltage applied across the conductor. Say the length of the conductor is L meter and current flowing through the conductor is I. Now, if you use a same cross-sectional conductor of length that is double of the previous one, that is 2L meter instead of L meter, we will find that the current becomes half of the previous currents, that is I by 2. If we further use lengthier conductor of same cross-section, we will see the current through it becomes lesser. If we observe carefully the current through the conductor for different lengths, we will clearly find that current varies inversely with length of the conductor. It can be concluded that current through a conductor for same applied voltage across it is inversely proportional to the length of the conductor. Hence, I is proportional to 1 by L. Say this is equation 1. Now, if we replace the conductor by a bigger cross-sectional conductor of same length, we will see the current is increased for same applied voltage V. If the cross-section area of our conductor was A and now it is 2A, we will find the current becomes doubled in the conductor for same length L and applied voltage V. If we further increase the cross-section of the conductor, the current will increase accordingly. If we observe carefully, we will find that the change in current through the conductor is directly proportional to its cross-sectional area. That means I is proportional to A. Say this is equation 2. Now from equation 1 and 2, we get I is proportional to A by L, and say this is equation 3. Let's see this from slightly different point of view. Now we know that current through a conductor decreases if resistance of the conductor is increased, and for same applied voltage V. This relation is linear according to Ohm's law. That means current through the conductor is inversely proportional to its resistance. That is, I is proportional to 1 by R, where R is the resistance of the conductor. Say this is equation 4. Now from equation 3 and 4, we get A by L proportional to 1 by R, or R proportional to L by A, or R equals rho L by A. Say this is equation 5, where rho is a constant depending upon the nature of the material, and it is known as specific resistance or resistivity of the material of the conductor. To determine the nature of constant rho, let's imagine the conductor has length L equal 1 meter and cross-sectional area A equals 1 square meter. That means the conductor becomes a cube whose edges are each of length 1 meter. Now putting the value L equals 1 meter and A equals 1 meter square, then R equals rho. Hence, resistance of a material of unit length having unit cross-sectional area is defined as the resistivity or specific resistance of the material. Now, unit of resistance is ohm, unit of length is m, and unit of area or cross-sectional area is meter square. Hence, ohm equals unit of rho into meter by meter square, or unit of rho equals ohm into meter square by meter, or ohm meter. This is the basic definition of resistivity, which comes from basic law of resistance. Hope you got a clear idea.
Resistors in series. A resistor is a material which offers resistance to the flow of current. Shown here are several types of resistors. Generally, in an electric circuit, a zigzag line represents a fixed resistor. Two thick dots at the ends represent brass terminals. In an electric circuit, resistors can be connected in series or in parallel. Resistors in series. Resistors are said to be connected in series if they are connected one after the other in the form of a continuous chain as shown here. Let us now calculate the effective resistance of the circuit. Consider three resistors R1, R2 and R3 connected to a battery through an ammeter. Observe the multimeter reading when it is used to measure potential difference across R1, R2 and R3. Now observe the multimeter reading when it is used as an ammeter. What do you observe? The current flowing through R1, R2 and R3 is the same, and that the potential drop V1, V2 and V3 across R1, R2 and R3 is different. Let V1, V2 and V3 be the potential drop across R1, R2 and R3 respectively. Under ideal conditions, potential drop across the resistors is equal to the sum of the individual drop in potentials. That is, V is equal to V1 plus V2 plus V3, where V is the total potential drop. Let us now calculate the effective resistance of the circuit using Ohm's law. Mathematical representation of Ohm's law is R is equal to V by I. In a series circuit, the potential drop across each resistor varies. Hence, we calculate the potential drop V1, V2 and V3 across the resistors R1, R2 and R3 respectively. The total potential V is equal to V1 plus V2 plus V3, but V is equal to IR. IR is equal to IR1 plus IR2 plus IR3. R is equal to R1 plus R2 plus R3. Therefore, the effective resistance of the circuit is equal to the sum of the resistances of the individual resistors in the circuit.
Resistors in parallel. Consider 4 resistors of resistances R1, R2, R3 and R4 connected in parallel as shown in figure. A source of EMF V is connected to the parallel combination. When resistors are in parallel, the potential difference V across each resistor is the same. A current I entering the combination gets divided into I1, I2, I3 and I4 through R1, R2, R3 and R4 respectively, such that I equals I1 plus I2 plus I3 plus I4. By Ohm's law, I1 equals V by R1, I2 equals V by R2, I3 equals V by R3, I4 equals V by R4 and I equals V by Rp, where Rp is the equivalent or effective resistance of the parallel combination. Therefore, V by Rp equals V by R1 plus V by R2 plus V by R3 plus V by R4. 1 by Rp equals 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4.
Kirchhoff's laws. Effective resistance of the simple circuits labeled A and B can be reduced to series and parallel combinations by using Ohm's law. But Ohm's law cannot be used to solve complicated bridge circuits having more than one source of EMF. To solve such bridge circuits, German physicist Gustav Robert Kirchhoff put forth 2 laws, namely Kirchhoff's first law or junction rule, Kirchhoff's second law or loop rule. Bridge circuits terminology. Junction. A junction in a circuit is a point where 3 or more conductors meet. Junctions are also called nodes or branch points. Loop. A loop is any closed conducting path. Kirchhoff's first law. It states that the algebraic sum of the currents flowing into any junction is 0. That is, sigma delta I is equal to 0. Consider a circuit having 5 current elements meeting at a point O with currents I1, I2, I3, I4 and I5. To take their algebraic sum, we assume the sign convention. The current flowing towards the junction is considered as positive. The current flowing away from the junction is considered as negative. Applying the sign convention, I1, I3 and I5 are positive and I2 and I4 are negative. That is, I1 minus I2 plus I3 minus I4 plus I5 is equal to 0, or I1 plus I3 plus I5 is equal to I2 plus I4. The total current towards the junction equals total current away from the junction. This law is in accordance with the law of conservation of charges. Kirchhoff's second law. It states that the algebraic sum of the potential differences in any loop must be equal to 0. That is, the sum of the EMF of the sources of energy in the circuit and the potential drop across the resistive elements is equal to 0. Let us see how the loop rule is used to solve the given bridge circuit. First, draw a circuit diagram to represent the circuit. Mark the direction of flow of current through each branch of the circuit. Then apply the sign convention. According to the sign convention, the EMF of the source is taken as negative if we move from the positive terminal to the negative terminal, and the EMF is considered to be positive if we move from the negative terminal to the positive terminal. The potential drop across any resistor is taken as positive if we move in the direction opposite to the direction of flow of current and vice versa. Consider the circuit shown here. In a closed loop, ABEFA, minus I1 plus I2 into R3 plus E2 minus I1 R2 is equal to 0. In the loop CBEDC, minus of I1 plus I2 R3 plus E1 minus I2 R1 is equal to 0. Comparison of the Kirchhoff's rules.